Now, after looking at the current voltage characteristics, let's look at few circuits with only DC voltages and currents. So we'll look at a few design and analysis examples of MOSFETs operating at DC. The idea is that we can use these examples to become comfortable in analyzing the MOSFET circuit quickly and effectively. For when we're dealing with DC, we will generally use the capital symbols, like for overdrive voltage in N MOSFET, we will use VGS minus VT subscript N. When we are dealing with PMOS, we will use the positive values and the capital again, but we'll be using the VTP values for that. Many cases we will ignore channel length modulation, which we would be easily able to see. In that case, we will use lambda is equal to 0. All right. So let's look at example 5.3. So we are given a circuit with two resistances, resistance on drain side, resistance on source side. So the circuit is drawn as this. So the arrow tells us this is NMOS, and we have two voltage sources. In this case, VDD is given as plus 1 volt, RD is unknown, there's current ID that's flowing through, we have drain voltage VD, there is source side resistance RS, and drain current is flowing there as well, and we have this is not ground, this is the source power supply, which is given as minus 1 volt. So there's the question tells us there is no length modulation, and we need to find RD and RS. These are the unknowns. So in this case, a few things are given. We are given the drain current 0.4 milliamp. We are given drain voltage 0.5 volt. Threshold voltage is given 0.7 volt. Mu n Cox is given as 100 microamp per volt squared. Length is given 1 micron. Width is given as 32 micron. So we have to look at the paths and see what are the voltages and how would those voltages show up across RD. So for RD, if I do my network analysis, I get the power supply minus drain voltage divided by the current that's flowing through. So straightforward, 2.5 minus 0.5 divided by drain current 0.4. So from here to here, we are looking at this part. So that gives us drain resistance 5 kilo ohms. Now, what is the operation of transistor. We don't know. We are not given that. But we can suppose and we can plug in the values and see what do we get. So let's suppose in this case we compare VDS, it has to be greater than VG. But here the gate voltage is given as, would be taken as 0. So that would give us the saturation region. So for saturation region, when you plug in the relationship, the formula, we would get ID. We know the ID, so we'll, by rearranging that, we'll find VOV equals to 0.5 volts. So of course we'll get VOV squared value, so we get square root of that, so we get 0.5. Now VGS is equal to threshold voltage, in this case VTN, plus overdrive voltage, which is 1.2 volt. It's 0.7 is given, and this is what we have just found from this. Now VG is 0 in this case. We haven't been given voltage drop on the gate side, so the source voltage is, to offset this, has to be minus 1.2 volt. Right, so from this relationship we get the source voltage. Now this will give us then the source resistance, which would be Vs minus VSS divided by the drain current. Now that's straightforward. We plug in the values, and minus 1.2 plus 2.5 divided by 0.4, we get source resistance as 3.25 kilo ohms. So this is the straightforward way to find our drain resistance and source side resistance. Now in the new edition, this same question is done with different values, but the procedure is still the same. Let's look at another example, and a little bit more involved, but if we know what we're looking for, it's pretty straightforward. So we have a circuit where two resistances are creating a voltage divider on the gate of the transistor, and two power supplies. One is on the same power supply is on the drain, and same one is on the voltage divider on the gate side. So RG1, RG2, and VDD is plus 10 volt, which is powering the drain resistance as well as the resistance network on the gate side as well. So we have source resistance. The resistance values are given, and we don't know what are the drain currents and what is the operation of the transistor. So let's start first by finding what is the gate voltage. So if you know the gate voltage, we'll be able to relate it to threshold voltage and see what is the operation for this circuit. So straightforward, if you want to find the gate voltage, we can look at this resistance, two resistances which are forming a voltage divider on the input side, and RG2 is which is towards the ground. So we would see what is the ground gate to ground voltage. So we'll find RG2 with the voltage divider. This is RG2 over RG1 plus RG2. So VDD is given as 10 and two resistances are given as 10 as well. So we find the gate voltage to be plus 5 volt. Now what is the, so here it is 5 volt, but we don't know what is the voltage on the drain, what is VDS. So we don't know if it is triode operation or saturation. So let's assume it's saturation. So, and then we'll see if the numbers make sense. If they make sense, we'll use those. If not, then we'll have to solve it for triode operation. In saturation, we know the basic fundamental requirement, VDS has to be greater than the gate voltage, and hence in that case we would use a simplified relationship of VOV square, and VOV over drive voltage we know is the gate minus the threshold voltage. All right, so what is the gate voltage? 5 volt, and to find the voltage at the source we can use this guy times the voltage times the current that's supposed to be passing through, which we don't know. So we can write down VGS is equal to 5 minus 6 ID. So voltage at the gate and the voltage at the source, they both should be related by this relationship. So this comes from, if we want to find the voltage at the source, that's current is ID, which is passing through 6 kilo ohms, and that would be 6 ID. So the difference of the voltage on the gate minus voltage on the source, that would be VGS. So 6 ID is what is the voltage drop across this resistance. We don't know ID, so we just write down the product of these two, just 6 ID. Now ID in saturation is given by the relationship half Kn prime, which is again mobility times oxide capacitance, W over L, VOV squared, which we can write the expanded form because we are not given the VOV, VT squared. So here we know everything, but we don't know VGS and we don't know IDs. Of course, this is the value we'll plug in here, so we'll get a quadratic equation, which simplified would be 18 ID squared minus 25 ID plus 8 is equal to 0. So we find the roots. Two values we get for ID from this equation is 0.89 milliamp or 0.5 milliamp. So we can plug in the values and see if it makes sense. So if we take 0.89 as the drain current, the source voltage would be 0.89 times 6, which in that case would be 5.34 volt. Now, if you look at it, that means the source is at higher potential than gate, which doesn't make sense because in that case, the transistor would be turned off, and that doesn't make sense. So hence we have to then stick to the value which is the smaller number. So we take that to be our drain current, and with that then we can find source. We know the resistance on the source side, so that would give us the source voltage, and that's plus 3 volt. Now the gate to source voltage is then gate minus source, which is 2 volt. Now if we want to find our drain voltage, which is on the lower side, this guy, we can take the drain, looking at the voltage drop from 10 volt, we are seeing voltage that's dropped on the source side. So we find drain voltage to be 10 of the power supply minus the voltage dropped on the drain side. So that gives us plus 7 volt. Now this is clearly fits the relationship that it is greater than the overdrive voltage. So hence the transistor is operating in saturation. Look at another problem. This is exercise 5.14. A simple transistor circuit is given. Here it is PMOS. The direction of arrow tells us it's a PMOS. There's a resistance on the drain side, and there is 1.8 volt power supply. So question is find R. That would result into an overdrive voltage of 0.6 volt. Threshold is given minus 0.4. Process transconductance parameter Kn prime is given, and width to length ratio is given. So we'll plug in those values when we look at the question. Now, source to gate voltage is, we know it's VTP plus VOV. So which is straightforward 0.4 plus 0.6, and that's 1 volt. So source voltage is 1 as the gate is at the ground. So that's the difference, and that's the voltage which is at the source. Now to find resistance, we need to find the drain current. So we can plug in into Ohm's law, where we can get the voltage across the resistance, which is 1.8 power supply minus the source voltage divided by ID. So from this we see that the drain to gate voltage is 0 because both of these are grounded. So in that case, we can see that the transistor is operating in saturation, where the drain voltage is definitely at higher level. So in this case, then we use the saturation relationship, which is ID equals half Kp VOV squared. So we find drain current from this. This is given, this is known. So ID is 1 milliamp, and we plug in the values here. We get 1.8 minus 1 divided by 1, which is 0.8 kilo ohms, 800 ohms. So this is how we would find the resistance for this